Welcome to the Unit 0 on proof techniques. This is a little primer on mathematical techniques and tools that we will just use a little bit on the side, but they're just very useful to know in general. It's a little bit of formal logic, if you like. Don't be too scared. It's not a lot and it's not very deep. But it's helpful to know the terms that I will show you, and it's helpful to know some of these proof techniques because they're used, again, in research papers, they're used in other classes, and they're used a little bit also in some of the material I want to share with you later in this module. So let's get started with the proof techniques. I'll show you some templates for proofs, and then specifically mathematical induction, because that's one that's heavily used in computer science and discrete mathematics. And I'll briefly touch on how to prove formally that a program is correct, that what you created in software is actually exactly doing the right thing. That's, again, a whole big area of verification. People are studying this in much more detail. I just want to give you a brief glimpse on it, because again, some of these questions will arise again when we discuss algorithms. So what is a proof? That's a very deep question once you think about it, and it has only really been settled in the early 20th century. So it's a fairly novel construction in this sense, where you stress formal. Of course, people have been doing mathematical proofs for decades and, well, dating back to ancient Greece. But they might not have had the very strict notion of a proof that mathematics now has. So what is a proof? A proof is a sequence of statements that say something about a certain matter, and each of these statements is either an axiom. That's a statement that you accept outside of the mathematical system to be true. So that's interesting. To get mathematics going, you have to accept, you have to believe, if you like, in certain axioms to make sense or to hold true. And there's no way for you to prove that these axioms are actually true or make any sense or anything like this. You have to accept them as given. Now then, of course, mathematicians wonder whether the weakest axioms that you can start with, and that's the subject of formal logic. But coming back out of the historical discussion, a formal proof is a sequence of statements, and each statement is either something that you accept to be true, God-given, or it follows from previous statements in this sequence using given inference rules. And these are usually very, very few rules that are allowed, and they're specified by the logical systems. All right, what does that mean for you and for us usually? Among experts in a field, often that's mathematicians, but it can also be theoretical computer scientists, or it can be programmers. They often also argue about proofs. It's often accepted that it's enough to convince another expert human that a formal proof is possible, that a formal proof can be written down, but you often don't write it down. Now, how can you be sure, how can you convince someone that this proof exists without writing it down? That's actually a bit tricky. Sometimes it seems like a proof exists, but it doesn't really exist. And so what you have to do is use formal logic as guidance against faulty reasoning, because that's something that easily happens, especially for beginners. So the easy way to convince someone that a formal proof exists is to write it down. And that's the only way to get bulletproof statements where you can absolutely be sure that it holds true. So let's see some more concrete examples what that means. And for that, we need a little bit of notation. So I think this is big enough. We will talk about statements. So these are logical sentences in English, or they can be statements about numbers with variables. So a simple statement could be A, which is the statement it rains, which is not true in my place at least. And another statement could be the street is wet. Okay, this is fairly vague. What street? I mean, also it rains is vague. Where? When? But let's suppose now and here where I am. And the street is wet. Well, the one outside of my window. Let's take this one. It's not really wet. So both statements are wrong for me at this point. But at a different time, they might be true. They might be satisfied. So usually statements are something where you can clearly say this is either true or false. It's hard to find examples in the physical world that are very clear-cut, either true or false. But in mathematics, it's usually easier. Either a number is equal to 5 or it's not equal to 5. There's nothing in between, really. If we have a statement, we can negate it. That means we put this funny symbol in front of it. And that is a new statement, which has just the opposite meaning. So not A is the statement that in English we would say that it does not rain. But in more computerized speak, you could just say it's not it rains. Well, sounds not great, but it's understandable. Then we can take two statements and use their conjunction, the and between them. That's written as this little roof. That's A and B. So it rains and the street is wet, which is true if and only if A is true and B is true. That's what and usually means also in the natural language sense. We can also put an or between the two. So this is true or this is true or both. It's the non-exclusive or, to use the term from there, which means it's allowed that both are true. Sometimes when we talk in English and we say or, we mean the exclusive or. It's either this or that, if you want to make the distinction clear. That doesn't have, in classical logic, doesn't have an extra symbol. Sometimes it's used and sometimes it's written as a with a plus with a circle around it. And it's called XOR. That's the exclusive OR, which has the meaning of either A or B, but not both. That's what I mean with either or. These are usually the things that are fairly natural and easy to understand. Now, slightly more controversial is implication. If A holds, then B is also true. If A, then B. If it rains, then the street is wet. That would be the example for our A and B. I have a nice question about that in a second, so I'll come back to that. But I want to mention the last one, the equivalence, written as this double arrow. And that means statement A and B are logically equivalent in the sense that A holds true exactly if and only if B holds true. And you can essentially define this as, in terms of the other symbols, okay, this is sometimes written as this. We define this to be the same as A implies B and B implies A. So that is the same thing as A is equivalent to B. The two are equivalent if one implies the other and the other implies the former. Okay, let's see a more concrete example. And for this, I want to ask you this question. So please have a think about this one. Is the following statement true? If the Earth is flat, then ships can fall over its rim. Take it as a logical statement and just tell me if that as a logical statement is true or false. I'll give you a sec to answer it and think about it. Okay, I see 26 people answered, so maybe another few seconds. Okay, 33. Again, remember, it's about participation. It's not about being correct about this. I will tell you. I haven't really told you what the answer to this is at this point in time. Okay, let's see. Does anyone feel he needs more time to think about it? Then shout out in the lecture back channel. Doesn't look like it. So here are the results. I think you can see them on the right, but just in case. So a lot of people say yes, but there's also a few that say no, and a few that say neither of the two is true. And I see, this is again, I can only show the correct answer if I leave it open. That's fine. So you can in principle still change your answer, but not much is learned if you do. So yes, the statement is true. And that's despite the fact that it talks about this nonsensical assumption. I mean, we know the Earth is not flat by now. We're pretty sure about this. At least most of humanity are pretty sure that the Earth is not flat. But for the logical statement, this means the entire thing is trivially true. So it's true because A implies B, again, is defined in terms of other things we already know. A implies B is the same as either not A or B. So in this example, A implies B. A is the Earth is flat. B is ships can fall over the rim. Now that means A implies B is the same as this thing, not A or B. Now we can read out what that means in English. It says, the Earth is not flat or ships can fall over its rim. Well, this is clearly not true, but this is true. And because it's an or in between, the overall thing is true. Oops. All right. So that's just one important notion. Just to keep in mind, this formal definition of implication is maybe sometimes not completely intuitive. You can totally make statements when the precedent, the thing in the if, is not true. You can claim anything, and it's still a correct statement. It's not a very useful statement in that the implication doesn't really do anything. That's logically true. Okay, I want to dive into a few more proof techniques, templates. So what these are for is, assume you have a statement that you would like to prove correct. You have, say, you found a cool new observation in an algorithm, and you'd like to show that a statement of the form, if A is true, then B is true, holds. You want to convince someone that this is true. What could be a more useful example? A useful example in our context could be A is the input to your program is valid, and I mean, this is whatever that means for you. Say a list of numbers. Then B could be the output of your program is what it should be, is correct. And then again, that has to be substituted in a concrete instance by something that makes sense. Maybe the list has become sorted. That's one of the topics that we will talk about in a couple of weeks. So that's one instance. Now you might have this situation. You want to make this statement about your program. If the input is a valid list of numbers, then the output is correctly sorted. You would like to prove this. Then you have different strategies how you could do this. You can do a direct proof. You assume that A holds, and you show that then also B holds. That's the obvious way to prove this, but there are other alternatives. So this is kind of I only listed because it's sometimes the way to go. It's sometimes the most convenient way to prove something, but it's not very surprising. The more interesting ones are the other ones, because sometimes this is hard to do. It seems not easy to show this, and some of the other strategies are easier. So one thing you can do is you assume that B is not true, and then you show A has also been false. So it's a proof by contraposition. It's similar to proof by contradiction, but it's slightly different in that you work your way strictly backwards. So assume your output of the program is not sorted. Then you show that something in the input was fishy. Maybe the input contains an invalid number that cannot be compared with others. Related is the proof by contradiction. That means you assume A holds and B is violated. And then you derive that this leads to a nonsensical statement. So classic examples in mathematics for this kind of proof are often that the square root of 2 is irrational. So you can prove that the square root of 2 cannot be written as a fraction of two integers. And one way to do is to assume, well, assume it could be written like that, and assume that the numerator and denominator are relatively prime. And then you can show by rearranging the equations that then actually they share a factor of 2. So that's a contradiction to your assumption. And lastly, sometimes it helps to make the statement more complicated to make the proof easier. So instead of just showing A implies B, you take a different condition C and distinguish two cases when C holds and when it doesn't hold. And if you can show in both cases that A and C implies B and A and not C implies B, then A implies B, either way. And you can have more than two cases as well. That depends on the exact statement, what is more convenient or more useful. Again, a little question for you guys. An example, and I would like you to tell me what proof template has been used there. So the example we're proving is if n squared is an even number, then n is also even. That is a correct statement, and one way to show it is you show that when n is odd, you assume n is odd, and then you show that n squared is also odd. What proof technique is that? What template did you follow for this little proof? And well, just while you're voting, this proof is actually fairly simple. When n is odd, that means you can write, I shouldn't use that arrow. That means n can be written as 2k plus 1 for some integer k, say a natural number. And if I now look at what happens to n squared, well, that's 2k plus 1 squared. That's nothing but 4k squared plus 4k plus 1. And you see that this is even because it's divisible by 2. And so it can be written as 2 times k prime plus 1. And k prime is again a natural number, and it's just this divided by 2. So that's the proof that also n squared is odd. So it's a simple statement, and the proof is clearly correct, though the statement is also true. But what proof technique have we used? Okay, we have 33 people. Maybe again, just a couple of seconds because this was a bit more reading necessary. Okay, 40-ish. Would anyone need more time? And out yourself in the back channel. Maybe we need this. You can't post anonymously to the chat rooms, unfortunately. Okay, 46. So I'll show you the results now. So most people voted for indirect proof, and we also have a couple of answers for the other things. The correct answer is indirect proof. And let me go back to the slides to show why. So that's, again, we should just identify A and B in this statement. N squared is an even number. That's our A. N is also even, or is even. That's our B. And now if you see, we start with N is odd, which was a bit mean because it's not directly the same thing as not B, but this is effectively not B because not even is the same as odd. And same here, this is again not A because again we flipped even and odd. So the proof technique we used is indirect proof. We showed the implication not B implies not A. All right, good. Thanks for the good participation in the question. And let's move on. There are other types of statements that we sometimes have to show. And one example is equivalences. We want to show that A is true exactly when B is true. That was this. So remember, that was A if and only if B, often written as this. So that's if and only if. So we can often prove both implications. We can often prove A implies B and B implies A as just two steps. So it's two little subproofs that together show that A is the same as B, is equivalent to B in this sense. And it often happens that one direction is much easier than the other, but not always. Another type of statement that we will sometimes need is about two sets. So we have a set S and another set R, and we'd like to show that R is a subset of S. Now, and just to make sure, this notation here with the bar below, this is somewhat similar to a less or equal sign. And it also means that R can be equal to S. And in logical terms, it means you show this implication. Whenever you have an element in R, that same element is also in S. So instead of arguing about sets, what you really have to do is prove an implication. And we've just seen how to do that. Scroll a couple of slides back and use one of the techniques from there. Now, this in isolation is not so often what we want to prove. It's more often that we want to prove that two sets are equal. S and R are equal as sets. And that again means you prove two inclusions. S is a subset of R, R is a subset of S. If both is true, then the two sets must be the same. So again, you have reduced proving set equivalence to set inclusion, which we reduce to implication, which you could reduce to one of the strategies that I've shown you. That's how proofs often get structure.